with these detectors at, let's say, a border crossing or at a port of entry, we're able to detect kind of that movement. So that's one part. Another part that's related to that is it's related to standoff detection. So in other words, what I just described is kind of a close field. So close as the truck is driving by, you detect it with maybe 20 feet, within 20 feet. So you have a big detector, it stays in place, the truck drives by at a border, and you detect if there's anything threat or not. The other one is if, let's say you can imagine you're in space, maybe. You're on a satellite, and you want to detect, okay, was there a nuclear detonation in some other country? Or is there some, I've also worked on projects where it's like, okay, can you be on a drone, let's say, and detect if there was a chemical warfare agent that was released in some country that you can't have easy access to? So it's these type of detection scenarios that involve, like that's the type of things that I work on. So we use chemical as well as spectral, that means using light. So using these signatures. Oh, jeez.
Oh, we locked in.
Yes, right. You didn't know this was coming, did you? So,
you said hazardous material.
Hazardous material, right? This is classified. No. So, yeah, so that's basically the scope of it, broadly speaking. And so we design either chemical analytes or the chemical compounds that are responsive to certain analytes. So we could say we're trying to detect a nerve agent. So we design the molecule that it specifically binds to a nerve agent and it has high specificity. Or we could say we want to detect the absorption of this frequency laser by this compound in the atmosphere, while ignoring all these background signals like diesel exhaust, like factory pollution. So it's basically finding the needle in the haystack, right? You need to find something that's specific and highly sensitive to these trace compounds or radiation signatures that are released. And so that's basically encompasses the scope of what I've been working
I was curious, on the radiation detectors, are they all mostly like near real time, truck driving by, or do you have some like integrated, over time?
Yes, right. So there's a variety of use cases. So the truck driving one, that's sort of a passive mode, and we're doing it actively monitoring mode, right? So it's sitting there waiting to detect something, and you have maybe that 1 kilohertz readout rate. So you're reading it out actively, and you're processing the data in real time.
Is the luminescence detection like solid state package along with the?
It's not they're moving towards it right now. They're photomultiplier tubes, just because they can do very large areas.
Super sensitive.
Yeah. But they're working towards like solid state silicon avalanche photodiodes or silicon photomultipliers. Is kind of the solid state's always good.
Can they see alpha and beta as well?
Yes, alpha is a little tougher just because of they have to package these things for the environment, but there is, so gamma, neutron, alpha, and they can do, some of these very large detectors do like neutrino detection as well. So that's looking at faraway reactors to see if they've upped their production to produce enriched weapon grade material or not. So it really goes kind of, you can look at it close and then you can look at it far, and it's all about the data processing at that point. So the materials enable the engineers and the physicists to write the algorithms to analyze the data, right?
Have any been reduced to little tiny like chip in a pocket?
Some of it. So there's concepts for that where you can do a lot of little detectors that are low performing, and then you do data fusion, and you get maps of how things are moving, or you do some really high performance detector that's fixed, or you do a really large detector that's kind of low performing but detects everything. So there's different paradigms for how you do it. But to answer the first part of your question, there's also things like treaty verification. So in other words, you could imagine globally there's treaties in place for nuclear arms and things like that. And so the IAEA, so it's International Agency for, I'm not exactly sure the acronym anymore, but it's basically they're in charge, they're not tied to any country, but it's an international consortium in charge of regulating treaties that have been signed by these different countries. And so those inspectors will go to a facility and say, okay, at this nuclear power plant, we're going to put this detector here, and we're going to see, are there any nefarious activities? Do you have a centrifuge that's running to produce plutonium for a weapon, or are you just making energy-grade material, right? A fuel rod that's used for the power plant. So these are the type of things that are integrated, where you log them over time, and you put in security features that are tamper indicated. So just make sure, okay, you put it there, come back in 6 months, you read out the list data.
Do any of your organic glasses have like metastable states, so they integrate it and then you release it, like thermoluminescence later?
Yeah, that's a good question. So not our glasses, but we have worked on things like that, like thermoluminescence, storage phosphors and things like that, where similar to kind of like the X-ray radiography, how they've used that for latent image processing. So you can store the image, then you either raster a light or raise the temperature, and then you release the energy, and then you can get an image of what, let's say, if there is something in cargo or your body, right? So this is used in medical imaging too. So really, it's pretty expansive. Like if you can detect the radiation, the idea is you can use it kind of wherever radiation is present, right? And so we're looking at different fields. Go ahead.
So I have two questions.
Sure.
First of all, are you guys something with the metastable state? That sounds like that can be really useful in a radiation patch detector.
Yeah.
And also, so are you the polymers and organic glasses that you guys are working with? Are you synthesizing them yourself, or are you?
Yeah. Okay. Yeah. Sure. So the first question, dosimetry is actually an interesting point. So I think that's what we talk about the badge detector. We haven't done that yet, but it's something that's on our radar because one of the areas that's not a part of the current slate of dosimetry is fast neutrons. And so the fast neutrons are natively produced by these certain fissionable radioisotopes. So for example, the people who work at nuclear reactors, it's an interest to have them wear a fast neutron dosimeter as well, because if you just do the thermal neutron, you're only capturing a small subset of the total neutrons that are emitted from that facility. So if you can directly detect the fast, you don't have to interpolate or sort of extrapolate what it would have been. You can actually measure it directly. So that's kind of on the idea of where we want to go, but it's not executed yet. Remind me your second question. It's
my second question is, are you guys working on like
synthesizing ourselves,
like novel compounds, or
right.
are you guys getting them from
right?
nature?
Yes. So everything that we do. So being a synthetic chemist, we do it design ourselves. So that's kind of its own story, and I may bore some of the business folks. So I'm sorry. But it's kind of its own story. So in other words, we start with, okay, what is the state of the art? So currently it's, let's say, polymers or a single crystal. So the polymers, it's like producing the table. You can cast the polymer, you can polymerize it in a reactor, you can produce it different ways. And then you add some things into it, it gives you these properties, right? The crystal, you get what nature gives you, right? You put a seed crystal, you have it of sufficient purity, and you control the environmental conditions, either concentration, temperature, so forth, sort of diffusion, stirring rate, and things like that. And if you're careful enough, you can grow a large single crystal. Or if you're not careful enough, you'll just get, you could think rock salt, right? It's just crystals everywhere, and that's not useful for this application. So because you need to get the light from one end to the detector, right? So it has to travel through basically a clear material, transparent material. So starting at those 2 points, our idea with the glass, which I think is most novel, is we design our molecules to try to behave similar to the polymer, which is basically these long tangled webs of molecules. But kind of like the crystal, where these well-defined packing of single molecules. And this gives good properties for this application. This doesn't. Tangled webs don't. So the idea with the glass is, okay, we're going to make this one, start with small molecules, we're going to design them a certain way so that they can't assemble on their own. Nature wants to actually put them in order. There's an energy associated with that that's released as you order it. What we wanted to do is design the molecule so that it's a small molecule. It's, let's say it's like this, as opposed to the long chain. It's like that, but there's no way for them to self-assemble because they can rotate, they can twist with respect to each other. So there's a lot of ways that they can pack, and then there's too much disorder, it's called. And so that gives you the properties, physical properties of the polymer. It's clear, it's isotropic, so meaning you can look at it from any direction and it'll bend light the same way. The refractive indexes are the same. Or whichever direction the radiation comes from, it still behaves the same. The crystal, you have, let's say, sheets that are packed like this, they're going to behave differently depending on which way you're coming from. And so, go ahead.
And you engineer that glass matrix to be especially sensitive to a certain energy signature, like linear energy transfer?
Oh, good question. Not by design, but by accident, yes. So he mentioned linear energy transfer. That basically means that a neutron reacts with hydrogen in a material. So hydrogen, you could imagine it's like organic molecules have carbon and hydrogen, right? So food, our bodies, tables, plastics, and the neutrons produce charged hydrogen atoms, and these are massive, they're heavy, compared to an electron, which is what the gamma produces. And then those energetic particles then ionize the material and produces light. What we want to do is make sure that there's big differences between the light produced by both of those. And so what we found is that the glass has been the largest difference of any of the materials that exist, but we're not exactly sure why. And so there's a couple ideas behind sort of hypotheses that we have, but really it's challenging to test exactly the basic reason.
More degrees of freedom. Rotation.
Yeah, right. It could be, yeah. And it also could be things, there's heteroatoms, so different atoms besides carbon and hydrogen. And so that may actually dissipate the energy of these electrons more than the protons. So that may actually cause that to behave differently. So yes, so it's unknown, but so far it's in the direction we want because the materials behave kind of in a novel way that's positive for the application. Good questions, by the way. Gail?
A little bit more simple question.
Okay.
But I think they'd appreciate hearing about how your curiosity as a child has been very, very valuable to you in you inventing and creating solutions to things that no one else has done yet. I think it's remarkable.
Sure. Yeah, okay. That's a good question. And I'll start the answer by, I think, referencing some of the, I hate to mention it in the same sentence as myself, but some of the great inventors, they actually are not tied to any one thing, right? So they have a natural curiosity. So you have like Feynman or Einstein or any of these folks, these really the giants of science. And they're really, they don't identify themselves as saying, oh, I do this little niche thing, right? They're big thinkers. And they say, okay, what's the problem? What is unknown about the world, right? And so I feel like the flavor of that, I wouldn't put myself even in the same universe as that, but the same flavor is true in my case, where what really put me onto the track of why I wanted to study chemistry was, okay, I like nature. I think the natural world is beautiful, it's amazing. How does everything kind of work together? The human body, plants. And then chemistry sort of provides some answers, right? So you can say, well, we do know, for example, that photosystem 2, which is responsible for photosynthesis in plants, is dependent on manganese ions. And there's 2 different oxidation states for manganese. And so we don't know why it works this way, but the ability for those manganese atoms and ions to shuttle between or switch between these different oxidation states is responsible for allowing plants to produce energy, right, and undergo photosynthesis. So it's kind of tying the two together, right? Because you have a partial explanation and you have the observation of the world. And so that drew me to it, is that chemistry gives you the sense of, okay, I'm trying to now step back and try to understand something that I can see, but I don't know why. And on the other hand, it also gives you the ability to create something that's never been made. Right? So, for example, with these organic glasses, the molecules that we synthesize, many of them, have never been made before, right? So we're able to do these discrete manipulations of matter, and nature doesn't do that, right? It doesn't do the specific reaction. So we can say, okay, whether it's useful or not, we came up with something new, right? And that sense of discovery really kind of is encouraging, because it's like a geologist going out and finding a new mineral, right? You could say, oh, I found this new mineral, now we're going to name it, or a paleontologist finding a new dinosaur fossil. It's basically the same kind of thing, except we have a higher turnaround rate. We can say, okay, I'm going to make something brand new today, and that might be my little success. And even if it's not useful, it's something that keeps me going, right? And then you can then extend that and say, well, maybe one of these new things that I make will be useful for something. And that turned out, like, for example, this is one. There is another example in graduate school where we discovered, or I synthesized a molecule that you're able to do quantum computing. And so I won't go too much jargon with that, but the idea is a hard drive is like you have a magnetic platter, right? And you have all these little bits, and the spin is either up or down, and you're controlling, okay, how does this encode? And in aggregate, the combination of all the bits, and you have binary data storage, you can either be up or down. You have two bits, 0 or 1. With the quantum molecules that I was synthesizing, even though they're not a consumer product, you can say now, well, I have 20 electrons, and we can put any combination of them up or down. So it's basically a factorial in terms of data storage or quantum, data processing or parallel computing. It's a long way before it goes into a device, but that's the type of thing that was interesting to me, because I said, well, looking at the state of the art, we can do this, right? And this is the next step. That if people want to shrink Moore's law and you want to get faster, higher data density, this might be the way, or one of the ways. So I don't know if that answered the question exactly, but it's sort of, all of that is basically based in wanting to know how things work. So taking apart stuff when I was a kid, deconstructing electronics, I think all of that stuff, breaking a lot of things in the process, but knowing, okay, what's the guts of this, right? How does this circuit, why does it work, right? Why does a microwave work the way it does? It's a simple design, but when I thought about it, it's like, well, I only knew how microwave worked probably in college. And it's something we use every day. It was made in, I don't even know, probably many decades ago. But if you really think about it, it's like, okay, yeah, I drive a car. How does the car exactly work, right? What are all the pieces in the engine? I use a microwave. How does a microwave, like, what is even the physics behind that? Or a computer, all of the technology is packed in. I think deconstructing all of that and trying to get some answers, I think that's what drives me to do something that's unknown. Right? So, rambling answer. Sorry.
No, I wanted them to experience your thrill of it.
Okay.
Yeah.
Yeah, go ahead.
So, aside from you're getting paid for your job, well, what are the things that motivate you to succeed today, and has that changed over the past 10 or 20 years?
Okay. Yeah, I think that's a really good question. So I guess I can say one thing. So looking, kind of preparing this a little bit, or even just self-reflection over the past couple years of where I'm at in life and so forth, it makes me realize a lot of these things fell into my lap, right? So it almost seems like there's a plan, when you see it on paper or on a slide presentation. It's like, somehow I knew as a high school student that I would be doing chemistry. And the simple truth to that is I had no idea. I didn't even know if there were jobs in chemistry, right? I just liked it. And then as I kept going, I kept having outs. I was saying, okay, well, I'll get a major in chemistry, and if it doesn't pan out, I'll maybe do pre-med, right, or something like that. And it's like a backup plan. But to answer your question, it has changed a little bit, and a lot of what I do motivates me now is actually motivated by solving problems. So before it was, I want the pure knowledge, right? I love doing research, basic research. I want to do this one thing. I don't care if it has an application, whatever. I want to do this because it's gratifying. Now I still have that, but it's a means to an end. So I say, okay, I want to take this from conception to a company licensing this from us, and we sell this and it makes an impact in the world. So, and I think that's an example of that is when I started out, scientific publications were the metric, right? That's success. It's like if you get lots of these and they're in good journals, then you're a success. You're going to get, as a professor, for example, you are judged somewhat on that. More recently, this is kind of where I'm spending a little bit more time is patents, right? So I want to invent something and provide that recipe or that formula to a company and then get them to produce it and then solve some problem. So I think that's kind of how it's evolved where I'm at now. And it's also related to why I took on this engineering kind of role, electrical engineering, because this is for making a national impact, to making the world safer, for example. So that's where I get the satisfaction on that one. This is going to be for the whole, let's say U.S. stockpile of nuclear weapons. You do this thing, and it makes it safer for 8 billion people or whatever many in the world, right? So that to me is, whether you're against or for nuclear weapons, that is, I think, the noble part of it. It's like, okay, I feel like this is better, because if it's ever stolen, then they're never going to get anything out of that weapon. It's dead to them. So the terrorists can do nothing with an American weapon. So that to me is like the satisfaction. So does that answer your question?
Yeah.
Okay, thank you. Yes?
So I have a question just about your work environment. So I imagine you're not always putting on the lab coats.
Yeah. More rarely these days.
So and I know it might even change over time. So like, are you typically in a meeting, typically sitting in front of a computer?
Yeah, that's a good point. So